Okay, the ratio test. I would say this is actually one of the most popularly used tests for infinite series, particularly in exams. So let me just briefly describe what it is. If you have a ratio of an, right, the general term an plus 1 over an, if that limit is approaching a constant that's less than 1, then we say it's absolutely convergent. Okay, if it's greater than 1, it's divergent. And if it's equal to 1, then it's no conclusion. Okay, so there's another theorem that looks very similar to this, and that was this one here. If you had an, and if you can find another one that you can compare with, bn, and if you do an over bn, right, and if this is some positive constant, now this time it just had to be any positive constant, then they're either both diverging or both converging. So don't confuse it with this one. It sounds very similar, right? This one is comparing the two. So I call this the comparison ratio test, and this is I just call it a ratio test because we're actually using the same term. Okay, so let's do an example of this. Okay, so test the series for absolute convergence. Here's what you do. So we know that an, we're letting an be this, n cubed over 3 to the power of n. Then an plus 1 will be n plus 1 cubed over 3 to the power of n plus 1. So if you have an plus 1 over an, right, we have n plus 1 cubed, okay, all divided by, right, n cubed over 3 to the power of n. It's compounded fraction. So let's make uncompounded, right? n plus 1 cubed over 3 to the power of n plus 1 times by the reciprocal of this, so 3 to the power of n over n cubed. Okay, so let's collect the the exponents of 3's together. So you get 3 to the power of n over 3 to the power of n. Let me write that as 3 to the power of n times by 3. And here we have n plus 1 to the power of 3 over n to the power of 3. So you can see right away that we can do some reducing here. 3 to the power of n, 3 to the power of n disappears. So we get 1 over 3. This thing can be raised all to the power of 3 as n plus 1 over n. Now as n approaches to infinity, that right there will approach 1. So the limit of this is going to be 1 over 3, which is less than 1, and therefore it's going to be absolutely converging. Okay, absolutely converging. Okay, so here's one more example. Determine the test for the convergence of this infinite series, and we can tell that we have to use the ratio test because of this n to the power of n, right? Along with n factorial. Think about it. We don't even know how to differentiate or integrate n factorial. And the only real way to compare this with anything else is through ratio. Okay, so let's let that be an. Then we get an plus 1 to be n plus 1 to the power of n plus 1, n plus 1 factorial. Okay, so we have n plus 1 to the power of n plus 1. Okay, this divide by, I'm going to multiply by the reciprocal instead. So I skip one step here. Okay, let's simplify this. That's n plus 1 to the power of n plus 1. That right there is the same thing as n plus 1 multiplied by n factorial. Okay, so we can reduce that, and we can also reduce this. Okay, that simplifies a lot. So we have n plus 1 to the power of n over n to the power of n. Okay, so we can put that all under one exponent of power of n, and we get n plus 1 over n. Okay, so this, let me split the fraction. You get 1 plus 1 over n to the power of n. That's going to approach E, right? By definition, that's going to approach E as n approaches to infinity. And E, E is, approximately 2.71, right? It's greater than 1. So therefore, the series is diverging, biracial test.